Good morning, myself Shiksha from BSc Chemistry Honors second year. Today we can read Organic Chemistry of Chapter 4 Nitro Compounds. Introduction. Nitro compounds are an important class of organic compounds which may be regarded as derived from hydrocarbons by the replacement of one or more hydrogen atoms by nitro groups. Nitroarenes, that is nitro compounds in which NO2 group is directly attached to benzene ring, can be prepared rather easily and have been used as synthetic reagents since long. But nowadays even nitroalkanes are being prepared and used on a large scale. Structure of nitro group. Nitro group is quite often represented as containing a double bond between nitrogen and one oxygen and a coordinate or dative bond between nitrogen and other oxygen. But actually nitro group is stabilized by resonance and it is hybrid of two equivalent contributing structures. You can see. The resonance hybrid structure is confirmed by the fact that the bond length of each nitrogen-oxygen bond is 121 pm or 1.21 angstrom, which is intermediate between NO single bond length 136 pm or 1.36 angstrom and N double bond O double bond length is this. In case of nitroarenes, resonance of nitro group with the ring can also take place, giving rise to additional contributing structure for the molecule. It will be interesting to note that nitro group is isoelectronic with carboxylate anion. Now nomenclature of nitro compounds. The nitro compounds are named by writing the word nitro before the name of the parent compound. The number of nitro groups and their positions are also suitably indicated as illustrated below. You can see nitromethane, nitroethane, 2-nitropropane, 2-nitro-3-methylbutane. And here you can see more examples. And now classification of nitroalkanes. Nitroalkanes are termed as primary, secondary or tertiary according as the nitro group is attached to a primary, secondary or tertiary carbon atom. That is primary nitroalkane, secondary nitroalkane, tertiary nitroalkane. एग्जाम्पल में है ये नाइट्रोइथेन प्राइमरी नाइट्रोएल्केन है, सेकेंडरी नाइट्रोप्रोपेन, 2-methyl 2-nitropropane. Now preparation of nitro compounds. Preparation of nitroalkanes. Nitroalkanes are usually prepared by the following methods. First step, vapor phase nitration of alkanes. This reaction involves the substitution of a hydrogen atom of the alkane by a nitro group. It is carried out in the vapor state by heating the alkane with nitric acid at about 700 Kelvin. See the reaction. RH plus HNO3 at 700 Kelvin results RNO2 plus H2 nitroalkane. Limitation of the process. During nitration of higher alkanes, all possible isomeric nitro products are formed. Moreover, rupture of carbon-carbon bonds also take place, leading to the formation of nitroalkanes containing lesser number of carbon atoms. For example, nitration of propane results in the formation of a mixture of 4 nitro compounds as shown below. You can see. Due to the formation of complex mixture of products, this method is not used for the laboratory preparation of nitroalkanes. However, this method is widely used for commercial preparation of nitroalkanes, since they are used as industrial solvents only. Now mechanism. The reaction is believed to involve the formation of free radicals, but the mechanism is not well established. Action of silver nitrite on alkyl halide. This is methyl generally employed for the laboratory preparation of nitroalkanes. When heated with silver nitrite, alkyl halides undergo nucleophilic substitution to form nitroalkanes along with small quantities of alkyl nitrites. RO and double bond O. This is because NO2 negative is an ambidient nucleophile. Here you see reaction mechanism. Third है oxidation of amines. When an amine in which the amino group is attached to a tertiary carbon atom is oxidized with potassium paramagnet, a tertiary nitroalkane is obtained. कैन सी अमाइन की रिएक्शन करवाई 3 ऑक्सीजन के साथ KMnO4 की प्रेजेंस में टू गिव tertiary nitroalkane. And now preparation of nitroarenes. Nitroarenes are almost invariably prepared by direct nitration of arenes. The nitrating agents generally used are concentrated or fuming nitric acid, mixture of concentrated or fuming nitric acid and concentrated sulfuric acid. Sometimes fuming sulfuric acid is also used. Third point, a mixture of concentrated nitric acid and acetic anhydride or boron trifluoride. Acetyl nitrate CS3CO into ONO2 obtained by mixing nitrogen pentoxide and acetic anhydride. Fifth, nitrogen peroxide in the presence of anhydrous aluminum chloride. Choice of nitrating agent. The choice of nitrating agent to be used for nitration of a given compound depend upon the following two factors. First, a nature of compound to be nitrated, or second, a number of nitro groups to be introduced. In the nitration of aromatic compounds containing electron releasing or activating groups such as NH2OH and CH3, the reaction takes place readily at room temperature by employing concentrated HNO3. In some cases, even dilute HNO3 can be used. For example, you can see for nitrating compounds containing electron attracting or deactivating groups such as COOH, or when it is desired to introduce more than one nitro group, a suitably strong nitrating mixture has to be employed and the reaction is carried out at a high temperature. It may be remembered that nitro group itself is also a deactivating group. Nitrobenzene and M-dinitrobenzene, for instance, can be obtained from benzene under the conditions shown below. M-dinitrobenzene बेंजीन से HNO3 और कंसनट्रेटेड H2SO4 के साथ रिएक्शन करवाई तो हमारा M डाइनाइट्रोबेंजीन मिलेगा, और बेंजीन की अगर हमने कंसनट्रेटेड HNO3 की 328 केल्विन के ऊपर करवाई तो हमें नाइट्रोबेंजीन मिल गया. मैकेनिज्म ऑफ नाइट्रेशन. Nitration of aromatic compounds like other aromatic substitution reactions is electrophilic in nature and involves a nitronium ion NO2 positive as the attacking electrophile. The mechanism may be summed up as follows by considering the nitration of benzene with nitric acid, sulfuric and mixture. Generation of electrophile HONO2 plus 2HSO4 formation होगी nitronium plus H3O positive plus 2HSO4 negative. Formation of carboxylate ion. Third, a proton transfer from the carboxylate to yield the final product. Now, evidence in favor of the above mechanism. It has been above that the aromatic nitration involves a stepwise mechanism. The nitronium ion, which acts as the electrophilic reagent, is generated in a preliminary step and brings about further reaction in two steps. The first step is slow rate determining step involving the addition of nitronium ion into the aromatic ring to form a carbocation intermediate. The second step, which is relatively fast, involves the elimination of a proton from the intermediate ion by the heterolytic cleavage of CH bond. The mechanism has been fully supported by isotope tracer technique as explained below. If an aromatic compound labeled with deuterium, the heavier isotope of hydrogen having a mass of 2 AMU, is subjected to nitration, it is found that the rate of substitution of deuterium is the same as that of ordinary hydrogen or protonium. In other words, no isotope effect is observed. Since a carbon deuterium bond is broken more slowly than a carbon protonium bond, the absence of isotope effect in aromatic nitration can be justified only if the rate of determining step of the reaction doesn't involve any cleavage of carbon hydrogen bond. This means that the final step involving the abstraction of proton through the cleavage of carbon-hydrogen bond cannot be the rate determining step. Therefore, the step leading to the formation of carbocation must be the rate determining step, as it doesn't involve any cleavage of carbon-hydrogen bond. Once formed, the carbocation loses the proton relatively fast to form the final product. The absence of isotope effect also rules out the possibility of a single-step mechanism for nitration. This is because single-step substitution cannot take place without the cleavage of carbon-hydrogen bond. As such, it must exhibit isotope effect. But this is not so in actual practice. Hence, aromatic nitration is a stepwise process in which the formation of carbocation is the rate determining step. Comparison of nitration of arenes and nitration of alkanes. It may be noted that nitration of arenes take place at relatively low temperature, whereas nitration of alkanes require a very high temperature. This may be due to the fact that the nitration of arenes involves the initial formation of an electrophilic reagent, while the nitration of alkanes is supposed to involve the initial formation of a free radical. The formation of free radical takes place through homolysis and requires stronger conditions than the formation of electrophile, which take place through hydrolysis. As such, nitration of arenes takes place more easily than nitration of alkanes. Nitroarenes cannot be prepared by the action of silver nitrate on aryl halide because of the very low reactivity of aryl halide towards nucleophilic reagents. Now, physical properties of nitro compounds. Physical state. Nitroalkanes are colorless, oily liquid when pure. They have pleasant smell and are sparingly soluble in water. With the exception of a few compounds including nitrobenzene, which are yellow oily liquid, all other aromatic nitro compounds are yellow crystalline solids. Nitrobenzene has an odor of bitter almonds and it is known as oil of myrrhine. Solubility and density. All the nitro compounds are heavier than water. Nitroalkanes are sparingly soluble in water, while aromatic nitro compounds are insoluble in it. They are, however, readily soluble in organic solvents such as alcohol and ether. Stability. When heated strongly, polynitro compounds decompose with explosive violence. Boiling point. Due to the presence of highly polar nitro group in their molecules, nitro compounds have strong dipole-dipole interaction. Consequently, they possess high boiling point, much higher than hydrocarbon of comparable molecular mass. However, most of the nitro compounds are volatile in steam. The melting and boiling point of nitro compounds gradually increase with the number of nitro groups, as illustrated. C. Now, chemical reactions of nitroalkanes. The important chemical reactions of nitroalkanes are as follows. Acidic nature. Tautomerism. Nitroalkanes containing alpha hydrogen atom, that is primary and secondary nitroalkanes only, exhibit acidic behavior and form salt in the presence of strong alkalis. For example, this. Acidity can be attributed to the fact that nitro groups has a strong electron withdrawing inductive effect. The anion formed after the removal of the proton from nitroalkanes get resonance stabilized due to the ability of nitro group to accommodate negative charge as shown below. It is interesting to note that if the salt formed by nitroalkane is acidified at low temperature, the oily drops of nitroalkanes do not separate immediately. But we get another form of nitroalkane to know as acetynitro form, which slowly changes into the nitro form. See, this is due to the fact that primary and secondary nitroalkanes exhibit tautomerism, the tautomeric forms being nitro form and acetynitro form. The tautomeric equilibrium between the two forms lies almost completely towards the nitro form because it is stabilized by the resonance of nitro group. Acetynitro form is relatively stronger acid than nitro form. An important feature of acetynitro form is that it can act both as electrophile and as a nucleophile. Unlike primary and secondary nitroalkanes, tertiary nitroalkanes and nitroarenes do not have any alpha hydrogen atom. As such, they exhibit neither acidic character nor tautomerism. Reduction of nitroalkenes. Reduction of nitro compounds is one of the most important reactions. The reduction of nitro group takes place in stages as such below. The product actually obtained depend upon the nature of reducing agent and pH of the reaction medium. Thus, nitroalkanes can form different products on reduction to as given below. Reduction in acidic medium. When reduced in an acidic solution, nitroalkanes form primary amines. Second, a catalytic reduction or reduction with LiAlH4. Reduction with LiAlH4 or H2 in the presence of nickel, palladium or platinum catalyst also yield the same product. Here you see. Third, a reduction in neutral medium. If the reduction is carried out in a neutral medium, a hydroxylamine derivative is obtained. The hydroxylamine are readily oxidized to corresponding nitroso compound on warming with Tollens reagent, which get reduced to metallic silver. The reaction is used as a test for nitro compound under the name Baker-Millikan test. Now hydrolysis. When boiled with concentrated HCl or H2SO4, primary nitroalkanes undergoes hydrolysis to form carboxylic acid and the corresponding salt of hydroxylamine. Example नाइट्रोएल्केन है और नाइट्रोएल्केन का एग्जाम्पल प्राइमरी नाइट्रोएल्केन और सीधा नाइट्रोएल्केन का एग्जाम्पल है. Secondary nitroalkanes are hydrolyzed to ketones and nitrous oxide by boiling with concentrated HCl. Tertiary nitroalkanes and nitroarenes are not hydrolyzed by acid. Fourth, a Neff reaction. When sodium salt of primary and secondary nitroalkanes are hydrolyzed by boiling with dilute sulfuric acid, aldehyde and ketones respectively are obtained. The reaction proceeds through the Ac-nitro form of nitroalkane. In this reaction, the Ac-nitro form acts as an electrophile. Action with nitrous acid. Primary, secondary and tertiary nitroalkanes exhibit different behavior towards nitric acid. Primary nitroalkanes react with nitrous acid to form nitrolic acid, which dissolved in NaOH is produced in red solution. Secondary nitroalkanes react with nitrous acid to form pseudonitrols, which have blue color but do not dissolve in NaOH. Tertiary nitroalkanes and nitrobenzenes do not react with nitrous acid since they do not contain any alpha hydrogen atom. The above reaction can be used for distinguishing between primary, secondary and tertiary nitro compounds. Halogenation. When treated with halogen, chlorine, bromine in slightly alkaline solution, primary and secondary nitroalkanes undergo halogenation at alpha position. For example, you can see nitromethane on chlorination in alkaline medium gives trichloronitromethane CCl3NO2, also known as chloropicrin. Tertiary nitroalkanes do not undergo halogenation because they do not have alpha hydrogen. Condensation with aldehyde. Due to the presence of active alpha hydrogen atom in them, primary and secondary nitroalkanes undergo aldol type condensation with aldehydes in the presence of a base to form nitroalcohols. The reaction 6 and 7 proceed through the Ac-nitro form, which act as a nucleophile in these reactions. It's a Mannich reaction. This is condensation reaction which involves formaldehyde, ammonia or a primary or secondary amine and a compound having at least one active hydrogen such as primary and secondary nitroalkanes. For example, this. The reaction can be used for preparing nitroamines, diamines, etc. So our chemical reactions of nitroalkanes is completed. Thank you.